Joining our webinar today. We're going to give everyone just another moment to log in, and we'll be starting very soon. Well, let's go ahead and get started. Hello, everybody, and welcome to today's Better Buildings webinar. We're dedicated to bringing you the latest actionable insights from leading industry experts. Better Buildings webinars are a chance to explore the topics, technologies, and trends that affect your organization, as well as the efforts to accelerate energy efficiency strategies and reduce cost. Today's webinar is called Get Pumped, Improving Heating Efficiency Across Climate Zones. And before we dive in, there are a few housekeeping items that I'd like to go through. Please note that today's webinar will be recorded and archived on the Better Buildings Solution Center. We will follow up with today's recording and slides when they're available. Next, attendees are in listen-only mode, so you don't heckle me, meaning that your microphones are muted. If you experience any audio or visual issues throughout the webinar, please just put a note in the Q&A box located at the bottom of your Zoom panel, and our tech support team will be in touch. So my name is Stet Sanborn. I'm your fearless leader today and moderator. I'm a technical account manager and affiliate through Lawrence Berkeley National Lab out on the West Coast. So for all my West Coast attendees, I was going to do my best Robin Williams, Good Morning, Better Buildings, but I'll hold off. I'm a mechanical engineer as well as a licensed architect, and I do a lot of work within the decarbonization world. For today's agenda, I'm going to give a brief introduction of just heat pump technology, and that should take about 5 to 10 minutes. And then we're going to jump into the people that you're really here to see. We'll go through a couple polls to get a sense of where all of you are at, what part of your organization you represent. And then the speakers are going to dive in with the actual meat and potatoes for today's webinar. We'll end with some time for questions and answers, and I'll try to wrap up with some closing statements. So just to set the table and level set, because we know everybody's at a different place, as today's webinar is based on heat pumps, I wanted to give a little bit of an introduction for those who actually don't know how heat pumps work, but they love them anyway. So heat pumps are effectively a small mechanical device that it compresses gas and just moves it around in a circuit. On the hot side, where it's compressed, we can steal heat from that refrigerant. After an expansion valve, it gets very cold and we can pick up heat and collect it with that same refrigerant. So heat pumps always have a hot side and a cold side. Sometimes they reverse and they can switch which side is which, but in general, this is how it works. And the only energy input that we typically have is the compressor power associated with that motor in the middle that compresses the gas. Otherwise, a heat pump is really just moving heat from a place that it is to a place that it really didn't want to be, kind of against nature's natural progress. Next slide. So heat pumps, as I mentioned, move something from an area that's either cold to something hot, or again, it can reverse and take heat from somewhere that's warm and put it where it's cold. The effort or the energy in is that electricity. The heat pump efficiency tends to go down the bigger that difference is. So the more work that compressor has to do, the lower the efficiency tends to be. However, we can move a whole lot more energy with that compressor on the heat pump than we can with traditional things like electric resistance heating or gas-fired appliances. So a very small amount of energy, we can actually move several times that amount of energy using a heat pump. Next. Now, you've probably seen discussions of heat pumps and different types of heat pumps. I'm going to go through in a little bit some examples of that technology that you might see out in the marketplace. But in general, heat pumps are categorized by either air source or water source. In the case of air source, we're extracting heat from the outside ambient air and moving it into the building, in this case, in the heating mode. In summertime, we can actually extract the heat from inside the building and push it outside, even though it's very hot outside, using a reversible heat pump. But air source indicates what that source sink is. And it's typical, I'd say it's the most typical heat pump that we see, certainly in residential applications and light and commercial as well. Next slide. Now, you'll also hear things like words such as ground source heat pump, geothermal heat pump, water source heat pump. Those are all types of heat pumps that instead of using the outside air as a source for heat or sink for heat, we're using some sort of groundwater supply or interconnection with the ground. So in geothermal heat pumps, which are different than geothermal power plants, but a geothermal, a ground source heat exchange heat pump, we have a heat exchanger that's buried in the ground. So you'll see those U-tubes buried in bores spaced across your site. And we push either hot or cold fluid into that bore field to heat exchange with the ground and extract heat from the ground or push heat to the ground. And we use that as a means to heat or cool our building. We typically see in ground source heat pumps a much smaller delta T or difference between the ambient temperature in my building and the ground temperature. And so those systems tend to be, not always, but tend to be even more efficient than air source heat pumps, especially when we look at cold climates or extreme hot climates as well. Next slide. In the best case, though, heat pumps can be used actually in what we call simultaneous heating and cooling mode. And this happens typically in larger buildings where you have some portion of your building heating and some portion of your building in cooling mode. This can also occur if you are in a very hot, humid climate, but you also are needing to heat a pool or heat domestic hot water. Simultaneous heating and cooling actually uses both sides of that heat pump. And one side, I steal the heat to make, say, my pool warm or domestic hot water warm, while the other side, the cold side, is actually providing simultaneous cooling in the building. This is the best case of both worlds. I'm getting heating and cooling and using both sides of that effectively within my building. And these systems, whether you hear them called heat recovery chillers, heat recovery heat pumps, simultaneous heating and cooling heat pumps, lots of different words that you might hear them called, these systems are the most efficient. We'll see coefficients of performance or efficiency values over 6, sometimes as high as 12. And those systems are exceptionally efficient because you're using or valuing both sides of the heat pump. Next slide. So I want to give you a sense of the flavors, because really heat pumps come in a whole host of menus, and not all heat pumps are created equally. And so the type of heat pump application that you might have in your building is really dependent on how you tend to move heating and cooling around, the heating and cooling energy around your building. There's 3 major categories. Hydronic, often is sort of considered like the old school way of moving hot water or chilled water around your building, but definitely most common in larger commercial buildings where you might have what's called a 4-pipe system, hot water source, return, and cold water, chilled water source and return. Those hydronic systems mean that your heat pump is likely standalone. It's a monoblock, it's an enclosed system, and it sits maybe in a mechanical room or on a roof or out on a pad. But the distribution inside your building is quite classic and all hydronic, maybe fan coils, radiant, things like that. For refrigerant-based systems, there's actually a refrigerant circle that moves through your entire building, actually lots of them. So these would be seen typically when we hear of VRF or VRV systems, variable refrigerant flow. You have a compressor unit that sits outside and a bunch of fan coils spread out throughout the building, and they're literally taking that entire refrigerant circle and circulating it through the building. And then for those of you who have, I would say, typically low-rise buildings, maybe an office building up to a few stories, you might actually have air distribution as your sole means of moving heat and cooling throughout the building. So you might have rooftop package units or equipment like that, and it's just lots of ductwork running through your building. So for each of these types of distribution, there's a heat pump for that. And so we'll go through some of the technology that you might see in those different applications. Next. So I did want to add just a couple of the words that you might hear out in the industry that might lead you to understand which types of this distribution you have in case you don't know in your portfolio. So if you have a hydronic system, water-based system, it likely will be paired with maybe radiant heating, radiant cooling, chilled beams, hydronic fan coils, trench convectors, baseboard radiators. There's kind of a lot of that technology that's all water-based. And depending on what climate zone you're on, you might have more likelihood to have one of those distribution methods. For refrigerant-based systems, or VRF, you might hear it called VRF or ductless mini splits or multi-splits. That's kind of the distribution technology names that you might see. And then for air-based systems, you'll likely have variable air volume, dual duct VAV, constant air velocity, or maybe just a single zone rooftop package unit. So those are some of the flavors that you might see of each of those system types. Next. So depending on which system you have, you're likely to have different types of source or the heat pump of how you make heating and cooling your building. You have air source heat pumps, which would be considered air to water or air to refrigerant. You may have very big central systems like a chiller, cooling tower, possibly with heat recovery. And then classic old school for heating of a building would be used of boilers. Boilers are only one direction and can only provide heating. Next. So if you've got a bunch of those rooftop package units, the transition technology, there's a huge credit goes to the Department of Energy for their cold climate rooftop package unit accelerator project right now, partnering with industry. But you'll likely see a whole lot more heat pump based RTUs coming onto the market. There's a few out there. They're a little pricey right now, but the prices are certainly coming down. Next. If you have rooftop boiler units with air handlers, we're already seeing in the marketplace now a big shift to air handlers that have integrated heat pumps in them. So you'll see those oftentimes with heat recovery built in as well. Another choice is obviously going to VRF systems and pairing that with your air handler. But in all cases, we hope the systems are including either heat recovery or energy recovery, because those strategies can dramatically reduce the size of the heat pump required. Next. So if you have classic chillers and boilers for larger scale buildings, there's a ton of systems on the market now that are 6-pipe, 4-pipe, 2-pipe air source heat pumps, as well as heat recovered chillers for your large buildings and campus scale projects. These systems tend to be modular. You can scale quite a bit with the size of your building. And they're a great resource, especially if you're looking to get rid of a heating or cooling only system and go to heat recovery style configuration. Next. Okay, so that is literally the 11-minute intro to heat pumps. It's worth a 5-hour class on its own because heat pumps are that exciting. But before we dive into the actual speakers, I wanted to just like we do at Summit, encourage you to go to slido.com. If you can take your time to get there, go ahead and enter participant code DOE. And we're going to get everybody on there. And we're going to set up a few of our poll questions. So I just want to remind you that we are using Slido not just for the Q&A with the speakers, but also for your polls. If you'd like to ask the panelists any questions, please do submit them anytime throughout the presentation. We're going to hold questions until the end. So we'll hold all the questions there, and then we'll curate the ones. You'll actually have a chance in Slido to upvote the questions that you think are the most important. So hopefully I will see those, and we can make sure the panelists get a chance to answer them. So I think with that, we're going to go ahead and pop up the Slido polls. We have 5 questions that we're going to ask you guys today. And it looks like some of you are already in there. So the first question is, what sector does your organization represent? Are you with a governmental agency? Are you a contractor consultant? Are you in higher ed, multifamily, commercial, federal side? Let us know who you are. And the speakers, and especially during the Q&A, we can help tailor our questions to the folks that are out in the room. because right now we have 347 attendees, which is incredible. So we want to just make sure we know who is represented today. We'll go ahead and we can get to the next question. So what role best describe, or what best describes your role within your organization? Give a shout out to my engineering friends, although they're just the quickest to respond. Lots of program managers, which is great, consultants, and really nice mix. But again, a shout out for all the engineers who want to hear about successful deployments of heat pumps and high efficiency equipment in buildings. So the gauntlet is thrown for Phil and David. Great. Let's go to the next question. And this is okay if you don't know, but we do want to know what climate zone your organization is mostly in. And so for those of you that have large portfolios, you might be a portfolio manager and have portfolios that spread multiple climate zones. Go ahead and list the one that's, I'd say, covers most of your portfolio. Otherwise, if you're a public agency, go ahead and, if you can, enter essentially where in the country are you? A lot of 5A, 4A folks. So these are our mixed climate zones, both mid-Atlantic as well as going up into sort of colder areas, including Chicago, areas with solid seasons. So that's exciting. So we can talk about heating, cooling, dehumidification, all of our favorite things. Fantastic. Thank you, everyone. Next question. So go ahead and also enter now, what challenges has your organization experienced when trying to implement heating efficiency technologies, which may include heat pumps, they could include other upgrades to increase efficiency. And I imagine that our speakers today are going to have some of the exact same questions or challenges. Cost, financing, cost, funding. Yeah, I think we're when we get the word cloud going from all the responses, I imagine there's going to be some similarities. Great. And I think we have one more question. Yes. So what successes have your organization had when implementing heating efficiency technologies? Anything that's actually gone well? And if you do have success stories that have gone well and you want to share them, by all means, you can use the Q&A tag to share your success stories. And one of us might follow up and ask you more about them. We're always looking for success stories to share out with Better Buildings partners. So when we have them, we like to celebrate them. So this is great. Well, we really appreciate input from everybody. I think that was our last question. Yep. So let's go ahead and switch back to the webinar. So we have a phenomenal lineup today. If you haven't had a chance to hear from Phil or David before at Summit or one of our other webinars, you're missing out. So really excited to have you attend and have both of these speakers share out their stories today. So first, our first speaker is Phil Mertens. Phil is a senior MEP project manager for Columbia Association, and shout out to Columbia Association. They're one of our most active Better Buildings partners and share both successes and challenges, which we love deeply. Our second speaker today is David Kaiser. David comes to us from the city of Alexandria and is a green building engineer for the city and has some case study projects that I was lucky enough to see him present at this year's summit. So I welcome both Phil and David. We really look forward to both of you sharing your stories with us. And with that, I'll hand things over to Phil to introduce himself and to kick us off.
Thank you, Stet. So I'm Philip Mertens. I am the Senior MEP, Mechanical, Electrical, and Plumbing Project Manager for Columbia Association. Columbia Association is located in Columbia, Maryland. That's smack dab between Baltimore, Maryland, and Washington, D.C. So we have a wide range of temperatures throughout our region. Next slide, please. So our heat pump project overview and development examples are varied due to the nature of our buildings. Next slide. So a little bit of background on CA. We are nearly 600,000 square feet of commercial building space. These buildings range from 100,000 square foot athletic sport and fitness clubs to 1,500 square foot daycare buildings. We have community buildings with theaters. We have ice rinks. It goes on and on and on as far as our quite diverse portfolio, as well as the type of buildings that we have are range from historical in nature to purpose-built buildings that we have designed and developed as new structures. We have a lot of different package units and split HVAC systems. We've been involved in an aggressive energy management program and replacement schedule, along with our coordination and association with the Better Buildings Challenge. We just 2 years ago, we hit our over 30% reduction of energy usage over our entire portfolio. Next slide, please. So some of the examples of these dual fuel heat pumps in lieu of gas and cooling package units are dual fuel RTUs. These are basically units that we have decided to change out standard RTUs for a heat pump dual fuel that utilize the heat pump technology as the basis for heating and cooling. But due to our climate, we also have gas as auxiliary heat whenever we need it. Now, our temperatures can range from into 100 degrees in the summer to single digits in the winter. So there are times that we could use some gas to ensure operational needs. Next, please. Some other examples, we have utilized DOAS systems, which is a dedicated outdoor air unit with cooling packages. The DOAS unit supply the fresh air requirement for the building, and we also utilize ductless splits throughout individual spaces to help with space conditioning for comfort temperatures, which allows us to reutilize existing ductwork in the older buildings and newer buildings that we design that into the structure. Next slide, please. So examples, more examples of this is low ambient heat pumps and low resistant DX units. So this is replacing older split units with DX with low ambient specified to extend the heat range. Next slide, please. Again, more examples of trying to utilize heat pumps is in our domestic water heating. We've replaced older 40K standard domestic hot water units with heat pump type water heaters. They also utilize electric heat, but primarily these units are designed to use the heat pump. You can reduce the amount of electricity used for the resistance heat with most of the units. You can switch between full heat pump to partial heat pump to all electric, depending on the need that you have for that. Maybe a typical event, you may need more electric heat recovery. But also in looking at changing to heat pumps for water heating, for domestic water heating, you need to consider how you're going to ventilate, because you will get some cold air discharge from the units. Next slide, please. So again, we have utilized heat pumps for heating our spas and indoor and outdoor spas. Again, some of the issues that do come up that we have addressed are the cold air. In some of the situations, the cold air is welcome. In some of the others, we need to vent it out. So we have been able to scavenge power from existing equipment, as well as past energy savings that we've been able to gain more electricity in the facility. Next slide, please. So we use load reduction in one system to enable electrification of another. Some of these are where we have converted to LED, and that results in significant load reduction, which has allowed us to change from a fossil fuel water heater or a standard resistance heater to a heat pump water heater. Next slide, please. So again, some of the examples, we've gone from decommissioned, oversized, resistant-based systems to that were space heaters, hanging space heaters, and radiant space heaters, to ducted systems and by getting the reduction in electricity throughout the building has allowed us to utilize that electricity for heat pump equipment. Next slide, please. Key lessons learned. So meaningful electrification is possible with package HVAC systems using dual fuel units. And that's a simple change. It's just deciding that instead of your standard RTU, you utilize the heat pump technology. And you need to be creative in exploring solutions and operational practices. This is right sizing systems. Does your hot water need to be so aggressive? Looking at older systems and how they were used and how the buildings were used, sometimes you can garner more energy from not using or not having equipment as large as what was originally designed for the building. And look for ways to repurpose that energy, the energy that you get from the lighting, for heat pumps. Older infrastructure may have significant power for repurposing. Some of the benefits of past projects we have done have allowed us to even create capacity within a system, or identify capacity within a system for expansion for things like elevators that would have required total new electric service and upgraded electric service in some buildings. And then again, monitoring building conditions for system performance. These come from electrical surveys, and then also your ongoing monitoring of utilities.
Thank you so much, Phil, especially just for showcasing the great breadth of all of your examples. We really appreciate it. A quick reminder to our audience to make sure you're using the Slido, www.slido.com, and the event code DOE to submit your questions. For all of you that are looking at the question list in Slido, you get the chance to vote for your favorite. So we make sure that we address your favorite questions, and we can put David and Phil up against the gauntlet of the toughest questions. So with that, I want to hand it back over to David for our next speaker. You have the floor, David.
Thank you very much, Stet. You raised the bar high for us. Well, Phil and I are just acolytes to Stet's pastor, so we'll just sing praises about heat pumps. And City of Alexandria is very excited about heat pumps. We do a lot of heat pumps. Next slide, please. So yeah, we're definitely about changing our facilities, and there's a natural sort of churn of all kinds of equipment that needs to be turned over as systems fail. So that's one of the areas that we really focus in on when systems fail, because that's the time that it's most cost effective to replace and upgrade with slightly better systems. And so we can get some really good improvement out of our facilities and energy use reduction out of that. So that's kind of the context that we do a lot of our energy savings and upgrade systems when system needs to be replaced. Next slide, please. The context of how we go about doing this is really based on the Environmental Action Plan of 2040. There are 3 different sort of primary targets that we're really after: 25% use reduction by 2027, 50% reduction by 2035, and 100% electrification by 2030. So those are pretty stringent targets for us. We're a good way through our 25% by 2027. It's possible we could get there. We're just a little bit shy right now, but we still have a little bit of time left, so we'll see how we go. Next slide, please. So this is an example of a historic facility that we have in the City of Alexandria, built in the 1800s. Next. And it is, if you forward again, it is based on a heat pump system. That's the original, well, this specific picture is not the original heat pump, but it was originally on a heat pump system, but it relied heavily on electric resistance during the wintertime. And the summer efficiency was, it was okay. It was minimum code. So at the time that we needed to replace these systems, we decided to really focus in on our mechanical systems and replace them with the highest efficiency systems, heat pumps that we could find at the time that we installed them. And when we did that, if you go next slide, please, you'll see that the energy use, that turquoise line there, starts at about 35 EUI and then goes down to 23. So this is on a historic facility, and it's actually one of the lowest energy use indexes that we have for an occupied building. So that's pretty exciting. This building is used for events, and then also there's offices in here, and it's open during standard hours. So it's a great example of how to achieve heating savings, because we're using the heat pump more during the winter. And we also actually get a very good cooling savings in the summer due to the efficient compressor and surface area of the exterior condenser and evaporator. Next slide, please. This is a fun one. Again, another building built in the 1960s. It's an apartment building, and the way we changed it out into a air to hot water heat pump. This is 100% heat pump. There's no electric resistance backup. This is a standard exterior condenser on the outside of the facility, and it feeds an interior storage tank and circulates water throughout the building for all the domestic hot water needs of the facility. It's about 12 units in this facility, so the occupants can get all their needs, hot water needs met. One of the things that I'll notice from this slide and one of the learning experiences we had, the contractor was not necessarily as familiar with air to hot water heat pumps and didn't put a snow stand on it. So you'll see that condenser resting right on the ground, not what you should really be doing. It was actually too late by the time that we recognized that, but it's not only for snow. Sometimes there's splashback that comes off that ground, and dirt and that kind of stuff can go into the condenser. So it requires a lot more cleaning and that kind of stuff when you get rain bouncing up onto the end of that. So that was a learning experience for us. Next, please. And this is the result that you see after that heat pump hot water heater was put in. It was an initial gas direct fired, with a chimney flue atmospheric boiler, and we got about a 50% energy use reduction at the facility, roughly, for installing that heat pump hot water system because it was so efficient. Next, please. Oh yeah, thank you. You can go forward. This is, again, another hot water heater. This is the before picture. And again, atmospheric, very similar to the previous one. You notice there's a big electrical resistance heater in this mechanical closet. And primarily the reason why this electric resistance heater was there, as far as I can guess, is that there's basically a hole in the ceiling. This is a mechanical room in the center of a building, a rec center, and so there's no exterior exposure except for this one punched hole of the exhaust vent that goes through the ceiling. So they felt that they need to put electric resistance in there, or a heater of some sort in there to make, risk tolerance and that kind of stuff. However, what that did provide us then, if you go to the next slide, please, is that we were able to remove that electric resistance heater because we could close up that vent if we put a heat pump hot water heater in there. So we closed up the flue pipe, no penetration now in the ceiling, no air can go in and out. And then we added some interior vents to the doors into that mechanical room so that now the conditioned space from the surrounding areas can enter in the mechanical room, so it doesn't have to be an isolated room per the manufacturer's recommendations. So this is really only used for kitchen and hand washing, so it's very easy to sort of downsize after measuring the amount of hot water that was used. In the previous example, we started with an 80 gallon and we were able to then use a 40 gallon heat pump hot water heater. So that was a good example. One of the other things I'll notice about this slides as I go through is that there's a lot of hot water heater changeouts, and the reason for that is that water heaters last the least amount of time of all the mechanical systems. So they change over a lot more, and so it's a lot easier to dig into those quicker. Next, please. Again, this is another heat pump hot water heater situation. Next view. And again, a large hot water tank, and then changed out to a reduced size hot water tank. This was in a library and had a recirculating loop that was on all the time. The use case was just for laboratories in the bathrooms, and one small kitchen sink for the staff. And so when we did this, we didn't really need that recirculating loop going all the time. There's just not much risk associated with having a pump be off on occasion when the facility is not used. So that's actually a key concept when you don't have showers in place that might be related to more health standards. Next slide, please. This is an old facility, again, built in the 1800s. This is kind of an exciting one. This is actually dealing with regular space heating this time. Next slide, please. And these are the heat pumps that are serving this facility, about 12 people, 4 units. These are actually air conditioning units, not heat pumps. Next picture. And this is the boiler that is also serving that facility. So one of the exciting things about this is that we have two distribution systems. We have a refrigerant line system providing cooling to those apartment units, and then we have a hydronic boiler system. And what's exciting about that is that now we have two distribution systems. We have a refrigerant system, and then we have hydronic system. And because these are old buildings and they have to get, things eventually break down and get changed out, the boiler is breaking in this specific instance. What we're going to do is we're going to get rid of the boiler and change these air conditioner units to heat pumps. And there can be cold climate heat pumps now that those are officially available. We can get low temperatures or high output at low temperatures. We can completely get rid of that boiler and rely on one distribution system. So one cooling plant at the roof provides heating and cooling through one distribution system. So now we have capital cost savings associated with not having to replace the hydronic system in this facility. You do have to pay attention kind of closely to how many BTUs you're getting out there, but that can be determined with appropriate looking at the nameplate data, and then also following manufacturers extended performance data, and then timing of how often those systems come on and off. So that's an interesting case study. Next, please. And this one is something I was just working on the past 4 days. We're just putting this in. Unfortunately, I didn't get the picture in time because literally it just got finished yesterday. But this is another hot water system in a commercial facility. And this is kind of standard in the mid-Atlantic region and maybe even other commercial buildings. But when you have a boiler system feeding a relatively large facility, mechanical engineers at the time were like, well, you've got a heating source already. Let's just reuse the heating source you have and put domestic hot water on it. The problem is that now you've obligated your space heating boiler to provide your domestic hot water heating energy all year round. So next, please. Oh yeah. And this is just sort of me showing the what is there, the existing system. This is an indirect heat exchanger that provides energy from the space heating and the boiler, and then transfer that over into boiler tanks. And then we've got a recirculating hot water pump. So next, please. So one of the things that we're doing is we're separating those two. Oh, could you go back one real quick? There, that's fine. We're separating the boiler, if you see there on the right side, is going to get separated from the domestic hot water system on the left. All right, next, please. And so this is what we're going to put in place. We're putting heat pump hot water heaters in there. So it's in the boiler room with the space heating boiler. So there's some residual heat coming off of that. And so these heat pump hot water heaters are going to be able to extract some of that energy from the boiler. And then let me show you the next slide with all the different kinds of savings from this specific separation of decoupling domestic hot water heater from the boiler. Obviously, we're getting heat pump hot water heaters. So there is some energy savings on just the application of a heat pump, COP of less than 1 and to a COP of around 3, depending on the capacity of that system. Next, please. We improve the condenser boiler efficiency. Some people don't recognize this, but actually just because you have a condensing boiler doesn't mean that you have a high efficiency system. It depends on your operating temperatures that you use. So if you go downwards towards 110 degrees or lower, that means you have a more efficiency boiler itself. So that provides some savings. Next, please. Pump savings are there by stopping the hot water pumps during the summer. So now we don't have to run the hot water pumps throughout the entire building when there's no hot water demand. So again, that's probably the biggest savings of this entire project is not the heat pumps themselves, but it's the pump for the entire building that we can now turn off because we don't need those pumps running anymore if there's no demand. Next, we've got heating savings by not continuously circulating the hot water. We've got heat loss through all those pipes going through all the buildings by having that pump on all the time. And then next, please, we also then have cooling savings because we just added heat to the building. Now we can remove heat. We have to remove that heat from the building. So by completely separating off the boiler and the domestic hot water, we don't have to have those kind of losses. And lastly, you know, altogether, these savings are estimated to save us around $10,000 a year for this facility. We'll see how that goes. So next, please. These are all the different kinds of heat pumps that we have. I'm just going to touch on them. Just like Phil was mentioning, we do dual fuel heat pumps, though with the new DOE cold climate rooftop unit challenge, we're hoping those come into fruition in the near future. And I can imagine a situation where we want to see those get implemented instead of dual fuel. One thing that I would notice in terms of lessons learned on the dual fuel systems, your mechanical contractors are going to basically do what they know. And if you have some performance basis that you want out of a dual fuel system, you have to sort of say, this is how I want the system to run. And then you have them walk you through it, because just because you have a dual fuel system doesn't necessarily mean you're getting performance that you want out of it. So just an FYI. And these are the lessons learned for my facility. Always plan ahead. This is one of the things that we did for the domestic hot water systems. We got 14 plans that a mechanical engineer put together for us, templates, so that when we have a hot water system replacement, that we can just easily grab one of those plans and then go through permitting a lot faster. Next. And then evaluate cost effectiveness. Again, we care about cost. And cost savings. So keeping the existing distribution systems is going to be very important to maintaining cost effectiveness, and then having the same plant on the heating and cooling system. Next, cold climate heat pumps, like I was talking about, are going to provide new opportunities for us, so that we don't need to use the boilers, or if we do keep the boilers, that they don't come on as often, because we can use those cold climate heat pumps. Next, please. Find the right team members and contractors. Some are going to be more used to doing novel things, and then also some of them are going to charge higher prices. So if you are cost conscious, you do have to look around, because the first person that provides you a price is not necessarily going to be the one that you want to choose. Next, verify performance. I already talked about this. Dual fuel heat pumps. You have to make sure that they operate correctly. The domestic hot water system, we've had a couple almost failures where the pumping distribution on the domestic hot water system caused issues, or either high energy or low water temperature. And by addressing those pumping issues after the system was installed, we were able to get the performance that we wanted. And lastly, don't give up. Keep trying. There are going to be some lessons learned in your organization, but keep learning from your own mistakes and other people's mistakes, and keep moving forward. So thank you very much. We're excited to have heat pumps.
Thank you, David. Wonderful as usual, and also especially the lessons learned. I feel like all of our design guides that we've helped put out are actually based in a lot of folks sharing failures early so that nobody else has to repeat them. So thank you to both of our presenters for your really insightful presentations. Before we transition to the Q&A, I wanted to encourage everybody in the audience to download our additional resources handout. It's actually being shared right this moment in the Zoom chat box. The handout contains links to resources from Better Buildings and our speakers on today's topics, and we hope you find these resources useful. So we're going to move into Q&A. We have a few minutes to jump in. I just want to encourage everyone again to go to slido.com, enter event code DOE to submit your questions and upvote. I'm going to dive right in. And some of you actually have addressed, between David and Philip, some of you have addressed these questions going in, but I want to make sure we give a chance for a little bit, maybe drawn out response. The top voted question is, how do you guys convince specifiers, the folks that you're working with, to move away from the same old, same old? Both of you guys are using an advanced sort of cutting edge technology. How do you convince your design partners to go with you on this journey?
Phil? Oh, all right, fine, I'll take it.
I'll follow up.
Okay, David first.
Oh, me first?
Yeah.
Okay, all right. So honestly, like, the easiest way to do that is to be the specifier. So I'm the project manager essentially. And so I care about these things, and I, learn from being an acolyte of Stet, all his resources that he provides, the things that need to be done in order to make a project successful. There's obviously some mechanical engineering knowledge that comes into play. I'm a certified energy manager, mechanical engineering background. Those things definitely help. But having those people on the ownership side that can advocate for that, and then really plug into, there's always questions that come back, and I don't want to, I could probably talk for an hour on how this is challenging, because I deal with, it's a complicated and difficult issue that's not always solved, and still not always solved. But having somebody on ownership be that advocate for you, and then has the ability to counteract some of the misconceptions that come through with data, and examples and all that kind of stuff, that I think that goes a long way.
What are you, Philip?
Well, I think you have to, one, I agree with David, being the specifier of equipment really helps. Also, having the foundation of support from the highest level in your organization on down, to aggressively go after these energy savings, and it's doing the right thing. I mean, that's really what it comes down to. We are very fortunate that we have that support, and that's where it starts. Starts at the top, when you have the support, and then of course there's the technical background that you need to investigate on your own. You need to know your buildings well and know where you can utilize the new technology, and where you can find that. That's the thing, is the treasures that you may already have in your buildings that you can go out and you can say, wow, well, we saved all of this here on our LED projects and our low-hanging fruit that we've developed over the years. Now, oh, wow, we can use this to, now we can get rid of some of these fossil fuel energy sources or uses, and we can adapt heat pump technology. And even some of the buildings that had been transitioned, you're transitioning again. We had some that were that were typical air handler units with total resistance electricity. There was no fossil fuel, so we switched those out to high efficiency heat pumps, and they were due to be changed. They were close to 20 years old, so it was time. And it's a matter of not just going with what's easy. For me, we have on-call technicians, and so they bid for that work. And part of that is also specifying, what you're looking for when you qualify those technicians. And that's part of it. And I think that's a big thing that David brought up is the same old, and trying to find people that actually know the equipment and know how to set it up.
Yeah, I'll jump in as a specifier, like as somebody in the private sector when I'm not wearing my DOE hat. One of the best things that you can do is, when you have your cohort of design teams that you work with, bring them to webinars like this, bring them to a summit, have them sit down with technical experts, because at the end of the day, when your engineer is comfortable with something, they'll do it. But if it's something they're unknown, it's risky. But the reality is that there are folks out in the industry who are deploying these systems really well. They've already gone through all the ways that they could do it wrong. I personally, when we did the thermal system decarb guide between DOE and ASHRAE, about, I'd say, half of the things not to do that are listed in there are because I did them. And I had projects that failed miserably. But we learned, and then we got the information out, and now engineers know how to tackle those problems. So bring a partner to the next webinar. and bring them into the fold because we need more designers and specifiers that can do this work. I think we have time for probably one or maybe two more questions. And if your question has not been addressed, we're going to be going through them and trying to get responses to folks. But for both of you, you talked a lot about the heat pump side. Could you talk a little bit about your experience with optimizing building envelopes or other upgrades that might have enabled that heat pump deployment or made the heat pump applications more efficient?
Yeah, if you don't mind, I'll start on this one. Uh, honestly, like we live in Old Town Alexandria, and so our buildings are old. They just are. And some of our buildings are historic, and the historic buildings don't get touched. And then there's also, zoning code, and there's, public perception, and then there's, all kinds of things that can happen. So envelope is definitely something that we want to think about and, shouldn't be ignored. Pause. That's also a very expensive upgrade and facilities that can never really shut down. Like, our facilities are used all the time. Like every single day, there's something in there, and, we can't like close down the facility without really harming the community. Envelope improvements can be very intensive, especially if you don't do the outside, which you're going to get into aesthetic concerns. Then you have to do the inside. If you do the inside, then you're talking about disruption of, activities. And so that's really hard. So unless you're changing like windows or roofs, or maybe some air sealing here and there, gaskets, that kind of stuff, it's very difficult for existing buildings to really upgrade the envelope without extensive planning and extensive, sort of whole building repositioning or change in occupancy and that kind of stuff. So that being said, there are opportunities. There's a facility that we have, a small recreation center that's the siding is starting to fall apart. And so we're going to redo the siding. Well, when we redo the siding, there's some good opportunities there for potentially insulated siding. There's some exciting products out there for that. There's some air sealing things you can do. Attics, standard attics, where you've got, so like your home, where you've got insulation right above the ceiling. You can do air sealing and insulating and that kind of stuff, and that can reduce the load. So yeah, there's good things that can be done, and it shouldn't be ignored. The hard thing is that when you have a mechanical system that fails, that's the time to strike. And that's where we end up finding ourselves, is that we have to replace things when they fail because that's most cost effective. So we're kind of doing all these things at once. It's where somebody I said, it's like we're sailing a ship while building it. We can't dock our ship. And so that's what's very difficult. And envelope is usually docking your ship.
I agree with that. Our facilities are constant use, and shutting down is definitely a planned event in any amount of renovation or even a changing out of a unit. It is definitely a planned event. While we are very aggressive in our replacements, I think, as I stated before, some of those areas where you can find treasures in the past projects that could be parking lot lighting that was, converted to LED. As you mentioned, David, roof replacements, adding insulation to a roof, window replacements. I mean, it could even be film that you put on a window. And then you look at all those things that add up. And even in the one example I gave where it was straight resistant heat, no fuel heat, no utilization of fossil fuels for heating. Just switching to the heat pump with a little bit of resistance backup is another energy saver, and that's like a self-contained win-win. But when you start to look at those other projects that you've done in the past, and and you do electrical surveys along with that. And I would recommend that as a basis for really when you start your design. Look at what you've done, do your electrical surveys, try to figure out what do I have that I can capitalize on. That is where that's where the real nugget is. That's where the gold is, and utilizing heat pump technology and having the energy in the building to do it.
Perfect. Thanks, Bill. And thank you both. I want to thank both of our panelists. We've come to the top of the hour. I want to thank you both very much for taking the time to join with us. Contact information is up on the screen. Feel free to contact our presenters directly if your question wasn't addressed. They've graciously agreed, so be kind to answer your questions. I encourage you to follow the Better Buildings Initiative on LinkedIn for all of our latest news. You can find all of the various handles for the various social media sites on the left-hand side of the slide. You will receive an email notice when today's recording slides and transcripts are available on the Better Buildings Solutions Center. And again, I want to thank our panelists for joining us and thank nearly the 400 folks that joined us online for this webinar. We hope you found this beneficial to your projects on your journey to energy efficiency. Thank you, everyone.